Today we are going to discuss about solution of differential equations. Determine the frequency response and the impulse response for the systems described by the following differential equations. d by dt of y of t plus 3 into y of t is equal to x of t. Taking Fourier transform of the above equation, we have j omega into y of j omega plus 3 into y of j omega is equal to x of j omega. Y of j omega is common, then it becomes j omega plus 3 into y of j omega is equal to x of j omega, or h of j omega is equal to y of j omega divided by x of j omega, which is equal to 1 by j omega plus 3. Taking inverse Fourier transform, we have impulse response as h of t is equal to e power minus 3t into u of t. Next problem, d square divided by dt square into y of t plus 5 into d by dt of y of t plus 6 into y of t is equal to minus d by dt of x of t. Taking Fourier transform of the above equation, we have j omega square into y of j omega plus 5 into j omega into y of j omega plus 6 into y of j omega is equal to minus of j omega into x of j omega. Taking y of j omega common, then we'll get j of omega whole square plus 5 into j omega plus 6 into y of j omega, which is equal to minus of j omega into x of j omega. After rearranging the above equation, we get h of j omega is equal to y of j omega divided by x of j omega, which is equal to minus of j omega divided by j omega whole square plus 5 into j omega plus 6, which is equal to minus j omega divided by j omega plus 3 into j omega plus 2, which is equal to a divided by j omega plus 3 plus b divided by j omega plus 2. Using partial fractions, we can find out the value of a and b, and we get a is equal to minus 3 and b is equal to 2. Then h of j omega is equal to minus 3 divided by j omega plus 3 plus 2 divided by j omega plus 2. Then h of t is equal to minus 3 into e power minus 3t plus 2 into e power minus 2t into u of t. Then convolution property states that convolution in time domain corresponding to multiplication in the frequency domain. Applying dual property, that is that multiplication in time domain corresponds to convolution in frequency domain. Then y of t is equal to x of t into h of t. If we take Fourier transform of that, we'll get y of j omega is equal to 1 divided by 2 pi integration minus infinity to infinity x of j omega into h of j omega minus theta into d omega. Multiplication of two signals is often referred as amplitude modulation. Therefore, this property is often referred as modulation property. Then x of t into h of t is equal to integration minus infinity to infinity x of t into h of t into e power minus j omega t into dt, which is equal to minus infinity to infinity 1 divided by 2 pi integration minus infinity to infinity x of j theta into e power j lambda t into d theta into h of t into e power minus j omega t into dt, which is equal to 1 divided by 2 pi integration minus infinity to infinity x of j lambda into integration of minus infinity to infinity h of t into e power minus j into omega minus theta into t into dt into d theta, which is equal to 1 divided by 2 pi integration minus infinity to infinity x of j lambda into h of j of omega minus theta into d theta, which is equal to 1 divided by 2 pi x of omega star h of omega. Next, we are going to discuss about concept of sampling. Sampling converts a continuous time signal into a discrete time signal. A discrete time signal is often derived from a continuous time signal by sampling at uniform rate. In the above given figure, we can say sampling period be tau and n is an integer, may be positive or negative, and x of n is equal to x of n tau, where n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Sampling theorem states that if a continuous time signal is sampled for all time at a rate fs, which is more than twice the band limit fm of the signal, the original continuous time signal can be recovered exactly from the samples. If the highest frequency present in a signal is fm, the minimum rate at which a signal can be sampled and still be reconstructed from its samples is above 2 times of fm, and the frequency 2 times of fm is called the Nyquist rate. When a signal is sampled at a rate fs, that means sampling frequency, the frequency fs by 2 is called the Nyquist frequency. Next, solve one problem. Find the Nyquist rates of the following signals. X of t is equal to 25 cos 500 pi t, which is equal to 25 cos 2 into 250 pi into t, where omega is equal to 2 pi f, which is equal to 2 pi into 250 is equal to 500 pi. The highest frequency or maximum frequency fm existing in the signal is 250 Hz. So the Nyquist rate is 2 times of fm, which is equal to 500 Hz. Then x of t is equal to 25 cos 500 pi into t. That is 25 cos 500 pi into t is equal to 25 pi into delta of omega minus 500 pi plus delta of omega plus 500 pi, where omega is equal to 2 pi f, which is equal to 500 pi, which is equal to 2 pi into 250. The highest frequency FM existing in the signal is 250 Hz. So the Nyquist rate is 2 times of maximum frequency, which is equal to 500 Hz. Next problem, x of t is equal to 15 rectangle d by 2, which is equal to 15 into u of t plus 2 by 2 minus u of t minus 2 by 2, which is equal to 15 into u of t plus 1 minus u of t minus 1. That is, x of t is equal to 1 when magnitude of t is less than 1 and 0 when magnitude of t is greater than 1 and half when magnitude of t is equal to 1. If we take the Fourier transform of the given function, we will get 15 into 2 times of sin omega by omega, which is equal to 30 into sinc function of omega. Since the sinc function has infinite frequency components, Nyquist rate is also infinite. Hence, rectangular pulse is not band limited. Next problem, x of t is equal to 10 sin phi t, which is equal to 10 sin of 5 pi t divided by 5 pi t, which is equal to 10 sin 5 pi t divided by 5 pi t, which is equal to 2 times of sin 5 pi t divided by pi t. That is 2 times of sin 5 pi t divided by pi t. If we take Fourier transform of that, we get x of omega is equal to 2 into 1 when magnitude of omega less than or equal to 5 pi and 0 magnitude of omega is greater than 5 pi, where omega is equal to 5 pi, which is equal to 2 pi f. The highest frequency present in x of t is 2.5 Hz. So Nyquist rate is 2 into 2.5, which is equal to 5 Hz. Next problem, x of t is equal to 2 sin of 5000 t into sin of 5 lakhs pi t, or x of t is equal to 2 sin of 5000 pi t divided by 5000 pi t into sin of 5 lakhs pi t, which is equal to 2 pi into sin of 5000 t divided by 5000 pi t into sin of 5 lakhs pi t. Using multiplication property of Fourier transform, we can write 2 sin of 5000 pi t divided by 5000 pi t into sin of 5 lakhs pi t as 2 pi into sin of 5000 pi t divided by 5000 pi t into sin of omega naught t, where omega naught is equal to 2 pi into 2,50,000, which is equal to 1 divided by 2500 into 1 when magnitude of omega is less than or equal to 5000 pi and 0 when omega is greater than 5000 pi into j pi into delta of omega plus 5 lakhs pi minus delta of omega minus 5 lakhs pi. This is from multiplication property. For minus 4,95,000 pi less than or equal to omega less than or equal to 5,05,005 x of j omega has values. Highest omega is equal to 5,05,005 which is equal to 2 pi into maximum frequency. Therefore, maximum frequency is 252.5 kilohertz. Hence, Nyquist rate is 505 kilohertz.